Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. Alkylation of 1,3-decarbonyl compounds under basic conditions. Moving on to the next step. Identify the substrate. Cyclohexane 1,3-dione is a 1,3-diketone. The methylene group at C2, flanked by 2 carbonyl groups, is highly acidic, pKa-5-7. KOH deprotonates this position readily to form a stabilized enolate. Moving on to the next step. Identify the electrophile. Allyl bromide, CH2 is equal to CH, CH2Br, is a primary alkyl halide that undergoes SN2 reactions efficiently. And for the final step, determine the site of alkylation. In 1,3-diketones treated with base and an alkyl halide, C-alkylation at C2 is thermodynamically and kinetically favored over O-alkylation under these conditions. KOH in protic or mixed solvent at moderate conditions gives predominantly C-alkylation. The enolate carbon, C2, attacks the allyl bromide via SN2. Product formation. The allyl group, CH2CH is equal to CH2, attaches to C2 of cyclohexane 1,3-dione, giving to allyl cyclohexane 1,3-dione. Both carbonyl groups remain intact, and no ring unsaturation is introduced. Match two options. Option B shows cyclohexane 1,3-dione with a CH2CH is equal to CH2 group at C2 with both C is equal to O groups retained and no additional ring double bond. This matches the expected C-alkylation product. Why other options fail? A shows O-alkylation product, enol ether with ring double bond, which is minor under KOH conditions. C shows a product with a ring double bond adjacent to the allyl group, which would require elimination, not expected here. D shows alkylation at C5, the non-acidic methylene, which would not be activated by 2 carbonyls and is therefore not favored. Therefore, the correct answer is B. Therefore, the correct answer is option B.